Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over a calorimetry problem involving an alcohol burner. So let's get into this. An alcohol burner creates heat by combusting isopropyl alcohol according to the following balanced equation. So here I have 2 moles of the isopropyl alcohol reacting with 9 moles of oxygen gas to form 6 moles of carbon dioxide gas and 8 moles of water. And here the heat of combustion, the enthalpy of combustion is negative 4,013 kilojoules per mole, okay, or per 2 moles or whatever it is. So it's per mole here, even though it's not written. Okay, so here it tells us that a 5 grams, there it is, 5.0 grams supply of isopropyl alcohol is burned, and the heat from the reaction is used to heat a mixture of 145.00 grams of ice and 250.0 grams of water. This ice water is initially at 0.0 degrees Celsius. If no heat is lost to the surroundings and all of the ice melts, what is the final temperature of the resulting water? And then they give us some information here. So, where do we begin? Well, the first place you want to begin is writing down all of the Q values that are involved in either absorbing or releasing heat. Because, again, we're assuming that no heat is lost to the surroundings, so any heat that's released must be absorbed completely by something else, and we got to list those things. So the first thing is we have a reaction that's giving off heat. So this reaction here is the reaction that is given off by the alcohol burner. So just imagine you have an alcohol burner underneath a beaker with ice water. The heat from the flame of the alcohol burner is burning the alcohol, the isopropyl alcohol, and that heat's being released and absorbed by the beaker of water, right? So heat is being released by the reaction, so we'll call that Q1. So Q1, the heat released, that's going to be the Q of the reaction. So the heat released by the reaction. Okay, what's the next thing? Well, we got ice water. The ice water is a mixture of 145 grams of ice. We're told that the ice melts. So the ice is absorbing heat in order to melt. So that's going to be Q2. So Q number 2, that's the Q, we'll call that Q ice. So that's the amount of heat absorbed by the ice to get it to melt. Okay, so we got Q1, we got Q2. Is there anything else? What else is absorbing or releasing heat? The water. It says that the mixture of the water, the heat is absorbed, the resulting water temperature, right? So once the ice is melted, all you have left is water. Well, that water can also absorb heat. So we're going to call that Q3. And we're going to call that QW for the water. And I think that's about it. Those are the only things involved in absorbing or releasing heat. Now we need to figure out what the relationship is and set up an equation. Now, normally in your simplest calorimetry problem, you've got two things. One is giving off heat, the other one is absorbing that heat. And so the way you would write it is Q1 is equal to Q2. And if Q1 is the releasing of heat, that would be negative. And so here, what this is saying is that all of the heat that's released by whatever's releasing the heat is being absorbed by whatever's absorbing the heat, right? So no heat is lost. So the magnitude of the heat lost or gained is equal, but this is negative because it's loss of heat. This is the loss of heat, right? So they're equal and opposite. Now here we have three things. One thing is releasing the heat, that's the reaction. and these two things are gaining the heat. So if we're going to make the loss of heat negative, then here we'd have Q1 is negative, and in this case, it's going to be equal to Q2 plus Q3. So plus Q2 and Q3. And so then you could plug everything into this equation and solve. That's fine. I like to move everything over to one side and have it equal to 0. So I'll add Q1 to both sides. And then this is going to cancel out. That's going to become 0. And that's going to be equal to Q1 plus Q2 plus Q3. So again, the Q1, that's going to end up being a negative amount, right? Once you plug everything in. And these two are going to be positive amounts because these are absorbing energy. But the total amount of Q1 and Q2 should be equal and opposite to the Q1. So when you add these together, it's going to add up to 0. So I like to use this form. So I'm going to use this one. Now that we have this one, you're more than happy. You're more than welcome to use this form. It should work out exactly the same way. There shouldn't be any problem. Okay, so I'm going to erase this and I'll put my equation up here. Equals Q1 plus Q2 plus Q3. Okay. Now I need to figure out what formulas I need in order to calculate each of these amounts of energy or heat that's lost or absorbed. So Q1 is the Q of the reaction. Let's start with that one. So the Q of the reaction, that's going to be related to the enthalpy of the reaction. The enthalpy of the reaction here is kilojoules per mole, right? So it's kilojoules per mole of propane or isopropyl alcohol burned. So this is going to be equal to delta H of the reaction. This is kilojoules per mole. I don't want moles. I just want an energy unit because Q is the amount of heat released. So heat is energy. The energy unit is going to be kilojoules or joules, not kilojoules per mole, right? So all I want is the absolute total amount of heat that's released by the reaction. So I need to get rid of moles here. Instead of kilojoules per mole, I want just kilojoules or joules. So I need to get rid of moles. How do I get rid of moles? I multiply this by moles. So if I multiply this by moles, and N is the number of moles, then the moles on the bottom per mole is going to cancel out with moles on top. So that's my formula for the heat of the reaction that is released. Now, one of the things is they don't give me moles, they give me grams, they give me 5 grams. So a couple of ways you could do this. You could convert the 5 grams of the isopropyl alcohol to moles using the molar mass of isopropyl alcohol as a conversion factor. Or another way you could do is you can remember that molar mass is equal to the mass in grams of your substance divided by the moles of the substance. N is moles and M is the mass in grams. So now I can solve this for N. So if I multiply both sides by N cancels out, and I get N times the molar mass is equal to the mass in grams. And now I can solve for N by dividing by the molar mass on both sides. Molar mass cancels out here, and I get the number of moles is equal to the mass divided by the molar mass, which is exactly what you do when you convert using a conversion factor, convert your mass to moles. I'm just now using it as a way of substitution. So now I can take this and substitute in for that. So this then becomes the enthalpy, the standard enthalpy of the reaction, multiplied, instead of N, I'm going to replace N with mass over molar mass. So it's going to be the mass over the molar mass of the isopropyl alcohol. And so then this is the formula that I would use for the Q of the reaction. So I can plug that in here. So I can erase this now. What about Q of ice? Well, the ice is going to melt. So melting is going to involve the heat of fusion. So again, notice that I have kilojoules per mole for the heat of fusion. So I got to do the exact same thing. So I'm going to use this formula. The only difference is instead of having the enthalpy, the standard enthalpy of the reaction, I'm going to have the heat of fusion of ice. So this is going to be equal to delta H of fusion multiplied by the moles of the ice. But again, instead of moles of ice, it's going to be the mass of the ice multiplied or divided by the molar mass of the ice. So here I'm going to put P for propanol, propyl, or isopropyl alcohol, so P, and then I'm going to put I here for ice. And now here's my formula for the Q of ice. Now if I replace this, so this is 0, Q1, Q2, Q3. Q1 is Q of the reaction. Q2 is plus Q of the ice plus Q3, which is Q of the water. Now, what's the formula for the Q of the water? Well, the Q of the water is the water that after the ice is melted. So one of the ways to make these sorts of more complicated calorimetry problems more easy to work with is to, or easier to work with, is to kind of compartmentalize the different steps in the problem, right? So although in reality, as the ice is melting and becoming water, the water is heating, absorbing energy. The new water from the ice is absorbing energy. The ice is melting, so everything is happening all at once. But if we can mentally separate those and think of them separately, it makes the problem a lot easier to deal with. So in this case, we're going to treat the ice as melting first without any absorption of heat by the water. Once all the ice is melted, then all you have is water. Then just use the total mass of that water, which is going to be the mass of the ice originally in the water plus the water you started with. All of that is going to be together in one mass, right? Then you can think of all the rest of the energy being absorbed by that amount of water. So we're going to use the Q equals MCAT equation for water. So this is going to be equal to the mass of the water, and that mass of the water is going to be the mass of the ice plus the mass of the water before the ice melted. Remember, the mass of the ice does not change just because it melted. So all that happens is that you start with 145 grams of ice, you end up with 145 grams of liquid water. That's going to be added to the 250 grams of water you started with. So that mass of water is going to include both of these masses. And that's going to be multiplied by the specific heat of water, which is multiplied by the temperature change of the water. And remember, temperature change is always equal to final temperature minus the initial temperature. This is really important because if you flip it, you're not going to get the right sign. It's important that you get the right sign because If you don't get the right sign, the calculation is not going to work out. So always final minus initial. Now that I have my formulas, I can plug everything in. So here, 0 is equal to Q of the reaction, which is going to be this here. So it's going to be delta H, standard enthalpy of the reaction, multiplied by the mass of the propanol divided by the molar mass of the propanol, plus Q of the ice, which is the heat of fusion, right? So it's going to be the heat of fusion multiplied by the same thing, the mass of the ice divided by the molar mass of the ice, plus Q equals MCAT. So this is going to be the Q of the water. So the mass of the water multiplied by the specific heat of the water. And then, of course, final minus initial temperature. So we'll just put that in. So final temperature minus the initial temperature. So now I have my full equation. So now all I have to do is just plug everything in and solve for the missing part, which is going to be the final temperature, right? So I have the delta H of the reaction, that's negative 4,013 kilojoules. Notice that I have joules here. Let's have everything be in joules. So I have negative 4,013 kilojoules, right? That's going to be per mole. 1 kilojoule is 1,000 joules, so I'm going to put 1 kilojoule on the bottom, 1,000 joules on top. Kilojoules cancel out. So this ends up being a large number, negative 4,013,000 joules per mole. Okay, so let's put that in. So this is going to be 0 is equal to negative 4,013,000 joules per mole, multiplied by the mass of the isopropyl alcohol. That is going to be 5 grams. So it's going to be 5.0 grams over the molar mass of isopropyl alcohol. And if I look that up or calculate it, 60.1 grams per mole. So this is 60.1 grams per mole. Now, it's important that you have the units there. Now, molar mass is grams per mole. So grams per mole needs to be written down. Okay, so I've got this part. Now I'm going to add this part. So the heat of fusion, again, is 6.02 kilojoules per mole. So same thing here. I had to multiply by 1,000 to get it to joules. So I'm going to convert that by multiplying by 1,000. That's going to give me 6020. So 6,020 joules per mole. So I'm going to put that here. So that's going to be 6,020 joules per mole, multiplied by, again, it's going to be the mass of the ice, and the mass of the ice is 145.00 grams. So that's going to be 145.00 grams over, and then the molar mass of ice, which is water. So the molar mass of water is going to be 18 point, here, let me fix that, 8. So 18.016 grams, and again, grams per mole. And we got our third part to add, which is this right here. I'm going to add that down here. It's going to be the mass of the water. Now remember, this is the mass of the water after the ice is melted. So it's going to be the mass of the ice that melted plus the mass of the water that was originally there. So 145 plus 250, that's going to give me 395 grams. So that's going to be 395 grams, or let me get this right. So this has 1 decimal point, this has 2, so this should have 1, because remember the rule is that when you add measurements together, the rule for adding and subtracting is that your answer should have the same number of decimal places as the least number of decimal places in the measurements you're adding or subtracting. And so they should have 0.0. So that's the mass of the water after the ice is melted, multiplied by the specific heat of water, which is 4.18 joules per gram degrees Celsius, multiplied by the temperature change. So we're told that initially it's at 0 degrees Celsius. And so we're trying to find the final temperature. So that's going to be TF minus 0.0 degrees Celsius. So now we have everything plugged in. So now it's time to just solve. Let's simplify. So we're going to multiply this together, but you look at the units. I have moles here, and moles there is going to cancel out. Grams here and here are going to cancel out, so I'm left with joules. So when I multiply this, I'm going to get a negative amount of joules. So let's go ahead and get that. 333,860. So this is going to be 0 is equal to 833. Let me see them again. Oh, 333,860. So that's negative 333,860. Let me double check. 333,860. That's going to be joules. Okay. Now, when we multiply, notice that sig figs, we got to pay attention to sig figs. Here, we originally had 4 sig figs, so this is the last sig fig. And here we have 2, and here we have 3. So 2 is the least number, and the rule is when you're multiplying and dividing, that your answer should have the same number of sig figs as the least number of sig figs in your measurements. Since the least is 2, then that's going to only allow me to have 2 sig figs here. So I'm underlining the second significant figure. The rest I'm going to keep to avoid rounding errors. So that's the first part. Now I'm going to do the same here. Same thing. Moles here and moles here are going to cancel out. Grams here and grams here are going to cancel out. And then I'm left with joules. So when I do this calculation, I get 48, 45, 1. So plus 48, 45, 1 joules. And again, since I'm multiplying and dividing, my answer should have the same number of sig figs as the least number of sig figs. Here, this is actually 3 sig figs because originally it was 6.02. So that was 3 sig figs. So the 2 is the last sig fig. So this is 3. This is 5. And this is 5. So the least number is 3. So for this one, 1, 2, 3. So I'm underlining that 4 to remind myself that that's the last significant figure. But I'm going to keep the rest because I want to avoid rounding errors. And then finally, I have this last one here. So I'm going to multiply these two together. If I do that, grams are going to cancel out. I'm going to end up with joules over degrees Celsius. And so when I calculate that, I get 1651.1. So I have 1651.1 joules per degree Celsius. Let me just double check. 1651, yes. And then this again, of course, is going to be multiplied by TF minus 0.0 degrees Celsius. Okay, so then I'm going to add these together. Notice I have joules here and joules here. I'm going to add that together. And when I add that together, I'm going to get negative 285,409. So that means 0 is going to be equal to negative, let me double check again, 285,409. So 285,409 joules. And what I'm going to do here is I'm going to just multiply this out. But notice that this is just going to be multiplied by TF, and then this is going to be multiplied by 0, and the degrees Celsius are going to cancel out, leaving me with 0 joules. So the zeros are just going to cancel out. I don't need to write that. So then I'm just going to write 1,651.1 joules per degree Celsius multiplied by TF. So now notice here, now I can get the joules on this side, add joules to both sides, so I can get TF by itself. So let's do that. So I'm going to add 285,409 joules. And then I'm going to add it on this side too, plus 285,409 joules. And then I end up with 0 plus this gives me 285,409 joules equal to, and then this. So 1,651.1 joules per degree Celsius. Now remember here, when I added these two together, I got this number here. So remember, the rule is when you're adding and subtracting, your answer should have the same number of significant figures, the same number of decimal places as the least number. Now, to be more accurate, it's not decimal places, but your answer should not be any more precise than the least precise measure that you're adding or subtracting together. What that means is that if you notice here, this measurement has the last significant digit is in the 10,000s place. Here, the last significant digit is in the hundreds place. This is more precise. So since this measurement has the least precise, because the last significant digit is further over to the left. So that means that this is going to control the precision or the significance of the digits in your answer. So that means that the 8 here is the last significant digit. So the 10,000th place is the last place of significance. I'll keep everything else. Now, what about this here? So here, how did I get this answer? Notice I have, this is the 3 decimal places, or 3 sig figs here, because this had 3 sig figs, this had 4. So, no, I'm looking at the wrong one. Sorry. So here we had 1651. So that one has 4 sig figs. This has 3. So then the last digit of significance is the 5 here. 1, 2, 3. Keep the rest just in case. So I'm going to underline the 5 here. So the 5 here. So now this has 3 sig figs. This has 2 sig figs. I'm going to go ahead and divide to get the answer. But I'm going to go ahead and erase everything up here to give myself room, since we no longer need this. We've done the calculations. So I'm just going to rewrite this up here. So we have 409. Don't want to transpose numbers here. 409 joules. Again, the 8 is the last digit of significance, is equal to 1,651.1 joules per degree Celsius. And, oops, I forgot, this is going to be multiplied by TF, multiplied by the final temperature. And then all I need to do is divide both sides by this to get temperature by itself, the final temperature by itself. So divide this by 1651.1 joules per degree Celsius. Divide this side by 1651.1 joules per degree Celsius. This cancels out, leaving me with final temperature. And joules are going to cancel out, leaving me with degrees Celsius. Degrees Celsius is a unit of temperature that matches. Everything looks good. So now all I need to do is divide this by this. And when I do that, I get 171, 72 degrees. Okay, so I made a mistake and I just realized what my mistake is. Now, everything worked out the same. Here's the mistake that I made. And of course, easy mistake to make, so don't make this mistake. Look here. This equation, this is the heat of this reaction for this particular equation. Notice how many moles of the isopropyl alcohol I'm burning. So this relationship is related to 2 moles. So the thing you got to remember is that the heat of the reaction is related to the moles, the coefficients. So since I have a 2 here, this is the amount of heat that's burned for every 2 moles, not 1 mole. I was assuming 1 mole, my bad, my mistake. So the only difference here is that instead of multiplying, where did I have it? So here I have the heat of the reaction. Instead of multiplying the heat of the reaction, this is per mole. This is actually for 2 moles. So if I'm going to get the per mole, then what I do is I'm going to, let's see. So that's for 2 moles. So I'm going to take the 4,013 kilojoules. And since this is for 2 moles, right, I'm going to use that ratio, right? So it's going to be 2 moles. And so I want per 1 mole, not 2 moles. So I'm going to basically divide this by 2. So if I divide this by 2, then I get 2,006.5 kilojoules per 1 mole. So then that's what you're going to use in your calculation here. So that is going to be in the calculation here. So if I'm going to leave this here. So when I do this calculation, let me erase this. So then this Q of the R is going to be, so it's going to be 0 equal to this heat of the reaction per mole. That's going to be the new 2006.5, or we want it in joules, so that's going to be 2,006,500 joules per mole. And then that was multiplied by the mass of the propanol, which was 5 grams over the molar mass, which was 60.1 grams per mole, right? So you should have that. So everything else is the same, dot, 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 plus, dot, 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 whatever else we had. So the only difference in the beginning was I had double this amount. So that this is what you should have for the actual number. And if you get this and you do the calculation just as I did before, what you should end up on this side for the equation, so this is going to be equal to 1651.1 joules per degree Celsius multiplied by the final temperature. The answer or the number you should get on this side is now going to be, give me a moment. $118,479. 118,479. And that's going to be joules. So that should be the equality you should end up with. Sorry about that. So be careful when you're given this equation. Easy mistake to make is pay attention to the number or the coefficient of the substance that you're burning, because the delta H is related to that number. So if you burn 2 moles of the isopropyl alcohol, you get this amount, but the delta H we want is going to be per 1 mole. So you would take this and divide it by this, or divide it into this, and then use that number. So if you do that, again, as I said, this is the only place where a mistake was made. Everything else, perfectly fine. You should end up with this, and then again, you're going to divide by 1,651.1 joules per degree Celsius. You're going to divide by 1,651.1 joules per degree Celsius. This is going to cancel out. Once again, we have joules canceling over here. We've got our degrees Celsius. And so if you divide this, then you will get, let's divide 1651.1 equals, you get 71.75. So TF is equal to 71.75 degrees Celsius. And again, as we said, you only have 2 sig figs over here. You have 3 there. So the least number is 2. So we need to round this to 72 degrees Celsius. So that is the final temperature. That makes a whole lot more sense than 130, 175 that I was getting before. So that, ladies and gentlemen, is how you do that problem. And again, anyone can make a mistake. So just make sure that you learn from my lesson here, you learn from my mistake, that pay attention to the equation you're given, and don't just assume that this is going to be per 1 mole. This depends on what your coefficients are here and what you're comparing to. We were interested in the isopropyl alcohol being burned, so here it's 2 moles, and so we had to take that into consideration. And so to get the kilojoules per 1 mole, you have to take this divided by the coefficient to get that relationship. And that was my mistake. Don't make that mistake. I hope this was helpful. Sorry about the confusion. If you enjoyed this video, if this helped you a lot, then please, by all means, like the video, share the video, hit that like button somewhere around here. Also, do me a solid. Hit that notification bell. Subscribe to my channel. When you hit the notification bell, make sure that you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, let me know. If you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.